Hey, North Beach physics students, it's me, Mr. Traer, down in my classroom by myself. It's immensely fun, guys. I just shot this entire chapter for you guys. I just spent 18 minutes talking, but I got a phone call the first minute and a half of me teaching this section, which stopped the video presentation. So round two, hopefully this works. I'm gonna go through chapter 19 liquids for you guys, talk about some of the principles in this. On the website, on Google Classroom, you guys are gonna see your website or your homework assignment, a short quiz, and some other videos posted soon. Hope you're all doing well. I miss you guys. I miss our interactions, our conversations, high fives, hugs, laughter, tears, all that. So I'm gonna do my best. If you guys don't hear me really well, or if you need more explanation, or this doesn't work for you, let me know, guys. I'm trying my best, and I hope you guys are doing well. So love you and I miss you. So let's start. Chapter 19, liquids. So when we're talking about liquids, most of the time when we're talking about liquids within science, we're talking about water since it's the most abundant fluid on this planet, okay? So within liquids, what we're talking about sometimes when we're talking about liquid pressure is the amount of volume of a fluid as well as its mass. So remember that mass divided by volume gives us our density. So if you have two identical containers, so let's say I had one that's half filled with mercury and one that's half filled with water, the denser the liquid is, the more pressure it's going to exert. So mercury in a glass, since it's 13.6 times greater than the density of water, the pressure exerted on the bottom of the glass will be much greater. But let's say we take two liquids of the same density and pressure, or sorry, the same density. If we have that, so we have two glasses of water, let's say a full glass of water and a half glass of water, the full glass of water, it's going to have a greater pressure because it's talking about the depth of water. That's what liquid pressure is all about. It's the amount of fluid above an object. So let's say you jump into a pool and you swim down 3 feet, your ears don't bother you. You swim down 6 feet, your ears don't bother you. You swim down to the bottom of the pool, let's say at 10 feet, and you start to feel your ears pop. And that's because the amount of fluid that's surrounding your head or under your entire body is getting greater. There's more water pushing down, in a sense, above you, which causes a greater pressure. Now, liquids are practically incompressible unless we have a temperature change. So as liquids heat up, they will expand. But if I took one of our little air syringes that we use here in science and I filled it full of water and there was no air in it and I put my finger over the end and I push really hard on the plunger, nothing's going to happen. I can't make that liquid get smaller. So it's an incompressible fluid. So as we work later on, we'll talk about hydraulics and how we're able to use incompressible fluids to do work. Okay, so liquid pressure at depth. So let's say you jump into the ocean and you swim down 5 feet. The amount of pressure that's exerted you at 5 feet in the ocean is going to be the same pressure that's exerted on you at 5 feet in a pond, inside your lake, if it was that deep, a river, estuary, anything like that. It doesn't depend on the amount of liquid. So if you have a gigantic ocean or a very small pond, it's about the depth of it. So water pressure depends on depth, not volume. So 2 glasses of water, one could be very skinny. You have a very tall graduated cylinder and a very wide beaker. The amount of water, as in the depth of the water, basically is how pressure is determined. Okay, so a dam holding back twice as deep of water than another lake must withstand greater average pressure regardless of the volume. One thing I'm going to pose to you guys is a question. Let's say you went to Lake Wainuchi. So you drive up there for the day and you notice at the bottom of the dam there's a small crack and water's coming out. If you stuck your finger into that small crack to stop the water, or to think you could stop water, would it work? So think about that question. If the dam is leaking and you put your thumb over that hole and it's a 100-foot dam, can you hold back the amount of water pressure there? So think about that question. Maybe do a little research on it. You guys can always make a comment down below in the little section or shoot me a message. It'd be awesome. Buoyancy. So the upward force an object exerts on something that's submerged. So you guys have played around with buoyancy before. You might have jumped into a lake and then you exhale and you start to sink, which we'll see again in just a bit within increasing overall volume. But it's the force that's pushing up on something. So if the weight of the submerged object is greater than the buoyancy force, it's going to sink. So a way of thinking of that buoyancy force is thinking about its overall density compared to the fluid it's placed into. So if it's equal to the weight of the buoyant force, the submerged object will remain at any level. This is something that's very, within buoyancy, it's very applicable to things like scuba divers. So they have to actually wear specialized weight belts to make sure that their weight is equal to the buoyant force of the water. Because if you're a scuba diver, and let's say you're taking some wildlife photography shots of a whale shark, you don't have to keep constantly swimming down or trying to swim upwards to be able to keep that buoyancy within the water column to take those videos. Okay? Okay, so buoyancy, the amount of water, or amount of space taken up by the number of water molecules, or sorry, let me start that. The amount of space taken up is equal to the volume of the object. So a way to think about that is, let's say I had this weird, crazy pencil sharpener that somebody left in my classroom, and I wanted to figure out exactly the volume of this object. So I could measure the length, the width, the height, I could try to come around the circumference or the radius of this, but my numbers aren't going to be exact. So if I actually submerge this in water, let's say I put it into a beaker of 500 milliliters of water, and it displaces, and the water rises to 550, it's displaced 50 milliliters of water. And remember that 1 milliliter is also equal to 1 cubic centimeter. So that would be 50 cc's. This would be 50 cc's, or 50 cubic centimeters of volume due to its displacement. Okay? And that's the same displacement that we use within engines. So 350 cubic inch engine, or a 1000 cc cubic centimeter motorcycle engine, that's all about displacement of the fluid out of those cylinders. Archimedes' principle. So Archimedes' principle ties together the whole idea of buoyancy and the relationship between the mass and the density and the volume of, or mass and volume of an object for its overall density. You guys will see a video on here. I will have a link on there about Archimedes' principle, the whole idea of the corona, the idea of the gold crown, and is it really good, or is it really gold due to its density? But Archimedes' principle is all about the equal amount of force pushing back up, or sorry, the amount of upward force on an object, and how much it's going to appear to weigh due to the overall force. So this is kind of a weird concept, but a way to think about this is being in a swimming pool and picking up somebody in a swimming pool, and they seem much less in weight. So I put a 300 gram block, weighs about 300 newtons when held in air. And let's say I put it in the water, and it displaces 2 newtons of water when submerged. Okay? So under the water, the block seems to appear less weight. It doesn't seem to weigh as much. But what it really is the apparent weight of the block under the water equals the weight in air minus that buoyant force. So the block of water appears to weigh 1 newton. This is the same way that you can be in a pool with somebody, and let's say they're 250 pounds and you're 125, but you can still pick them up with one arm as they're submerged in the pool. You can't pick them up above the water because there's nothing else supporting it, but it's that buoyancy force that's pushing upwards. So within sinking and floating, an object sinks if its density is greater than the liquid it's submerged in. So if you were to take an object, let's say a rock. So you've got a rock and its density is, let's say, 8.5 grams per milliliter, and you throw it into water, it's going to sink because water's density is 1 gram per milliliter. So if its density is greater than the submerged, or liquid it's trying to be submerged in, it's going to sink. But if you can sometimes change the overall volume of an object, sometimes you can actually make it float, or in some cases, make it equal within that fluid. So I just use a very simple example of Chasia. So we take Chasia, we throw her into a lake. She might sink. And you guys have played around with this before. You're laying in a lake, and you're on your back, and you exhale, and you start to sink, and your legs tip down, and all of a sudden your head's barely above the water. You're like, oh, I'm sinking. And you take a deep breath, and all of a sudden you start to rock backwards. Well, why you're doing that, in the same case of Chasia, is you're increasing your overall volume. Make sure my camera's still going. It is, good. So we throw her in the lake, she exhales, she starts to sink. Oh gosh, that's not good. But if, let's say, right before she hit the lake, she took a deep breath, she can float for an extended period of time. So that's because she's changed her overall volume. She's increased that due to air. So other animals and things that do this, submarines use ballast tanks. So they fill those ballasts either with air to let them float or water to let them sink. Remember, the submarines are made of steel. So if you add a whole lot of water into that steel, it's going to make it less buoyant than the force around it, and it's going to sink in that water column. Fish, a lot of times, use a swim bladder. So if you think back to biology, so these guys can adjust the amount of gases within that swim bladder to allow them to float, sink, or remain constant in the water. And things like crocodiles and alligators, sometimes these guys will eat large stones, and by doing so, they increase their overall density, making them sink in the water. And if they can get just right, their eyes are the only things that appear above the water, which makes these guys great ambush hunters. Okay, principle of flotation. So a floating object displaces a weight of fluid equal to its own weight. So if you're thinking about shipping containers and large vessels, when these things are made, so let's say you take a block of steel and you make it into a ship, it's going to displace a weight of water equal to its own weight. If it increases, it displaces water equal to its own weight or more, it's going to float. If it's less, it's going to sink. So this is why you have something that's steel, it has a very high density, but as you bend it and you make it outwards and make it into a vessel, its overall volume is greater than it was before as a packed little system. So that overall volume increases its flotation or buoyancy in the water. And last slide for you guys for today is Pascal's principle. So the Pascal's formula is all about force over area and within pressure. So remember when I talked about pressure for you guys, if you decrease the diameter of an object, you increase its speed. So we're talking about fluid in a system. So we have a hose, we decrease the pressure, we increase speed. If we increase speed, we decrease pressure. So it's a flip-flop, but this is the formula that we use. And an incompressible fluid does not decrease in volume when pressure is increased. Okay, so this is the whole concept of, let's say you are a civil engineer and you're developing a city. What size water pipes do you need to be able to transport water to every single citizen throughout the city? How big is that diameter going to have to be? How much smaller does it have to get throughout the city? And as it makes conjunctions or connections to other people's houses, how much smaller is that diameter going to be to increase the speed of the water to be able to get out of the faucet? So there's a huge connection within Pascal's formula in civil engineering and in just the world in general. So I hope you guys are doing well. Please reach out for help if you need anything, questions, concerns. I'm always around, I really am. I'm working really crazy hours, but I love you guys and I miss you. So hope you're doing well. I'll talk to you all soon. Peace.